the
This
paper.
is it's more related with the with a paper presentation. Yeah, you're right. Sorry.
Yes.
Okay. So okay, thank Marcel for being here, and the floor is yours.
Thank you. Well, as I was saying, today's my talk is like a journal club talk. It's also my exam for the class of Salvatore and Luca. So the paper that I picked to present to you guys is this one. Is a PRL from. Do you see my pointer? Let me go like this.
Yeah, we
Uh,
do. We do.
Yes.
okay, great. This is a PRL for 2023, and it's called Variational Quantum Simulators based on Waveguide QED. So this is basically a paper who talks about how you can engineer systems to build an analog quantum simulator to solve problems that classical computers can't do efficiently. So first, just to motivate why to study this, I think you all are familiar with the dimensionality problem, but let's go through it very quickly. So for example, if you want to simulate classically a single qubit, this is easy. You have a basis that is just two states, and you have a Hilbert space dimension of just two. If you have two qubits, this is too easy. You can even do this by hand. But if you go to n qubits, then the things start getting out of hand because the Hilbert space dimension grows exponentially with the size. And if I'm not wrong, with our best classical computers, we can't do more than 50 qubits. I mean, of course, I'm talking about like the full simulation of the system, not like using techniques like tensor networks or DFT. Those are also have some value to simulate those kind of systems, but they rely in approximations. We want to try to do stuff like with less approximation as possible. So the quantum simulation field try to tackle this kind of hard problems. So one specific case of quantum simulator that I'm going to talk is the analog quantum simulator. That is basically you have a controllable quantum system, one that you can control, can tune as you wish, and then you can use it to simulate other systems. You map your Hamiltonian or interactions for the system that you have interest to this kind of simulator, and then you can perform your evolution and do whatever you wish. So what they proposed in this paper is to build one using a waveguide QED system. So basically, this is the sketch of the system. This dark region here is a photonic crystal, a periodic structure. So that have a nonlinear dispersive band. So it's like this. So they also put emitters, quantum emitters coupled to them, like single level atoms, and they tune the frequency of those emitters in the band gap. So in that way, the photon that this emitter would like to emit doesn't have a way to propagate on the lattice, and we have bounces depict as but this shaded region. And as we know, they have like an exponential shape, and this we see that the parts that they overlap is like an interaction that we are going to have between the qubit I and the qubit J. And what they also do is they address this quantum emitter with lasers, and these lasers give some tunability to the system. So the nice thing is you can write the effective Hamiltonians for this kind of simulator, and they look like this, where J is the interaction strength, and the interaction shape is like going like this exponential, where xi and xj are the positions for each qubit. And the nice thing are they can tune this the J and the L, so they're not have to be fixed between the whole system. And this is the very nice thing that they're going to exploit in this paper. So what they use to test this kind of simulator is a toy problem. They try to find ground state for critical spin models. So they're going to consider the XXZ model at critical point that is given by this Hamiltonian, and the transverse field Ising model also on the critical point. And the technique that they're going to use to find the ground state is quantum variational algorithm. Let me go through it. Variational quantum algorithms lies in this big umbrella of quantum machine learning. So they work more or less like this. You start with initial state, and then you build a layer, and this layer is the all operations that you're going to perform on your qubits. And another in this layer will depend of a vector of this is a vector theta that depends, can be rotations, can be time evolutions, whatever. And then you repeat this layer d times. After repeat these layers, you have a matrix, a vector of vectors, a matrix of variational parameters. And then you need to have the best, you want to find the best parameters that give you a state or that solve a problem that you're trying to solve. For example, after doing this, after performing the circuit, you have an output state, and then you can define a cost function. A cost function is a function that will return a number and can be anything that is relevant to your system. So in this case, we want the ground state. So the cost function will be the energy. You want to minimize this cost function, and what we're going to do is, since this kind of algorithm is hybrid quantum classical, we're going to throw this cost function in a classical optimizer, and the optimizer will tune the parameters in a way that find the minimum for this cost function. So after the optimizer give you update parameters, and then we plug again on our quantum circuit, and this loop runs until we reach convergence, and the cost function doesn't change much anymore. Yes, so one thing important that you may notice is this kind of algorithm depends heavily on how you define your ansatz, right? So as a cartoon, I'm showing here the two types of ansatz. One, you have this blue ball that represents the Hilbert space, and then your ansatz is this region. This is all the possible states that your ansatz can reach. And ideally, you want your ansatz to overlap this green region that is the solution, because the solution that you want lies in this region. And well, one can think, okay, we can make the ansatz the more expressive as possible to cover all the Hilbert space, then just let the classical optimizer to find. That is the case of this to find the parameters. This is the case that I depict here. But the problem is, if you create this type of ansatz, you start having regions on this. I'm plotting the cost function landscape. So it indeed has a minimum because the solution is inside of the possible states that ansatz can reach. But you also have this flat region that called baryon plateaus. This region, the gradients vanish exponentially. So if your optimizer gets stuck on this, he won't be able to move away. So you're going to be stuck in a point that's not optimal. So the idea is to have an ansatz that is expressive enough to catch the solution, and that have a smooth cost function landscape that you can just let your optimizer start here, and he naturally goes to the bottom of the landscape. So okay, the ansatz that they study on this, right? The one that you can implement on that analog quantum simulator is this one. So they're going to use those kind of Hamiltonians to do this. You have these gates, right? W. This is the layer. They have these gates W that depends on T and L. T is just evolution time under one of their Hamiltonians. They're going to use the XX Hamiltonian for the XXZ model, and the Ising-like Hamiltonian for the transverse field Ising model. And on their layer, they also put single qubit rotations. So they have just an angle that you're going to rotate those qubits, and you have also the interaction length. Here is not telling you that this. Here here it seems that it's the same for all layers, but it's not. So each layer have a T and a L different, and the optimizer can find a combination of the interaction length and evolution times that find the best results. So yes, so we do that, and then they're going to compare this with the state-of-the-art ansatz that do this kind of stuff. So one of them is the hard efficient ansatz. That is basically you apply single qubit rotations, can be an X, Y, and Z direction, and then control NOT gates, and it is a single layer have this kind of structure. And the other type of ansatz that they're going to consider is the brick layer ansatz that use the same type of gates but have a different structure. And the other ansatz that they're going to consider is the Hamiltonian variational. They're calling the Hamiltonian variational. That's basically you assume nearest neighbors, and then you do a second order totalization of the Hamiltonians that I showed you of the models that you're trying to solve for the ground state. And they're also looking at the same as this, but when you do L going to infinity, because if you do L going to infinity, you have all-to-all interactions. So they want to see how this tunability capabilities that of this circuit can help or not in finding a ground state. So the main idea is these ansatz have tunable parameters, they're tunable interaction, and these ansatz have fixed interaction range. So now we can go to the results, and the results to compare this bunch of models. They use this metric of the infidelity that is basically 1 minus the overlap of the optimal state that optimizer give you with the actual ground state of the system that can be computed numerically. And then if you look here on the left, you have the transverse field easy model, and here you have the XZ model. For the transverse field easy model, let's start with this. On the y-axis, I have the infidelity. On the x-axis, I have D. D is the number of layers. Remember that the ansatz repeats the layers. So the idea is we want to do as with a minimum number of layers as possible. So you see that the yellowish ball here is the waveguide ansatz that they're proposing. The triangle one is the waveguide with the infinite range. The pentagon greenish is the first neighbors, just the second order totalization. The square are the hardware efficient ansatz, and the rhombus are the brick layer ansatz. And you can see at least in this plot, the waveguide is the dynamics of the waveguides dominates the other ansatz. You can reach much smaller infidelities by just considering by using these ansatz with tunable interactions. And this is more expressive if you look at this dashed line. This dashed line is when the infidelity is 10 to the minus 2. So that means that you have 99% fidelity. So if you look at how is the minimum amount of layers that you need to find the ground state that have 99% fidelity, and here they're comparing with different size of the system. This was run for, I forgot to put here, but for 12 qubits, I guess. And here they're looking for 6, 8, and 10. You see that the waveguide ansatz is the most efficient one that can perform this. And the same if you look for the XXZ model, they have this kind of the same behavior. The waveguide kind of does better, but here you can see that the brick layer is for circuits, deep circuits, they start to be better. But this happens only on deep circuits, and this is a thing that we don't want, right? We want to find the state, the ground state that we want with the minimum amount of layers, because these simulations were done by using a perfect case. There's no noise, so the gates are perfect. They can interact perfectly. There's no dissipation, nothing. So when you start to putting noise on your system, then we start losing this kind of results, right? So this is why we need to do this in with less resources. And indeed, if you look again at the line here with 99% fidelity, you see that also for the XXZ model, the waveguide also have pretty good results. You can reach this kind of this state with just 2 or at maximum 4 for n equals 16. You need 4 layers to do that. And yeah, as I was saying, if you put noise on your system, what happens is for deep circuits, then the results start to getting messy. So you see that when you add noise, the waveguide ansatz that they're proposing are still much better. And of course, we can't reach that much infidelity like in the previous plots, like here we're going to 10 to the minus 5 almost, but I mean, in the presence of noise, you still have a pretty good infidelity.
Sorry, Marcel, which kind of noise is that?
The noise that they're using, if I'm not wrong, they're using amplitude damping and dephasing. So after at each application of the gates, they can have a probability of get dephased or damp a little bit the signal. I guess this is the if I'm not wrong, this is the noise that they use.
But it is the intended as the natural noise of the circuit because they are.
No, this is intended to be the type of noise that you can have in a waveguide-like platform, because the idea is to propose ansatz that can be run in a waveguide type of. So this is the type of dissipation that you can have, kind of stuff.
Sorry, another question.
Okay.
Do they say the amount of time needed to train these models? When you increase it might take longer or something.
This is a good question. They don't mention this, but while doing my period abroad, I work with them with some similar stuff like this, with variational quantum algorithm. That's not this presentation because it's an ongoing project, and we're doing like trying to find spin squeeze states. But I remember talking to one of the authors, that's the first author, and apparently for I don't know, can take a week to train like a very large model, like 16 qubits for 11 layers. That can take that much, and using a cluster, not a simple computer. Yeah.
There is no study of the amount of time.
No, on this paper, no. Unfortunately, no.
And another question: the training uses the exact value of the infidelity, right? Like, so you change the value of the parameters. And
yes, because when you change the parameters, when you change the parameters, you change the states that are going to overlap with the ground state, right? The ground state is fixed. You find it numerically, and it's there. And then you run the optimizations and find the best, and then you have the state, right? And then you compute the overlap of them, and this is what they call infidelity.
The reason I ask is because if you imagine doing this, sorry, I'm speaking very slow because I hear myself speaking. When you implement this experimentally, you wouldn't know exactly this fidelity, right? You would need to estimate it from data, and that there is another source of noise.
Yeah, exactly. In this case, they're doing like a toy example just to test their model. It's not like, I mean, indeed, there's no way, if you're trying to solve the problem that you already have the solution, that's not much sense doing that, right? But yeah, I think in this case, they should have other methods one should have other methods to control how good or how bad this is going. I mean, what I can say in the other problem that I was working, we didn't know what was the best result that we want to find. What we're looking is looking when the optimizer saturates, right? So they're going to go a curve like this, and then when it doesn't change anymore, and then would be, I mean, we're happy with a state that is close enough from what we're looking. So yeah, I think the idea is not to find exactly the ground state, but a a good enough state that can be used like as a ground state. I don't know if I was clear. But okay, so let's continue. So when you add noise, then this get very messy. So the other analysis that they did in this kind of system is, okay, we are looking to critical spin models that have short range interaction, right? It was nearest neighbor interaction. So they consider also the long range transverse field easy model that they're written by this, the Hamiltonian is written by this, and then the data give you the value for the critical values, and again they study this in the critical regime. And the important thing is now they have this power law type of interaction between the spin. It's expected, since the ansatz that they're doing have long range interactions, that they're going to perform better, right? And what they can do also, they introduce a new type of ansatz that is depicted here in green, the waveguide power law, that they can create this power law like interaction by just doing a sum of the exponentials that they already naturally have on their system. So this is the results that they found. Again, now they test for alpha equals to 1/2, 1, and 3. There is the exponent of this parallel interaction. And again, looking, you can see that the waveguide and the waveguide with the power law are by far the best compared to the others, except for when you look for alpha equals to 3. For if alpha equals to 3, you see that the bricklayer have a result for a deep circuit, but again we have that problem, right? We don't want deep circuits. We want the stuff to be done with the less resource as possible. So if you look at, again, that plot of 99% fidelity and look at the minimum amount of layers that you need to the ground state for this system, you see that the waveguide and the waveguide of power law by far is still winning. Not in this case, the waveguide power law loses a little bit in the case of alpha equals to 3. And yeah, this, I mean, we can reach the conclusions here already. Is, well, the waveguide platform that they propose have a tunable range interactions, and they can be exploited to improve quantum algorithms. And at least these long range interactions for this kind of problems that finding ground state for a critical spins model seems to find best results with less resources. So yeah, that was a quick talk. So thank you for your attention.
Okay, grazie. Thank you, Marcel.
Just remove this to see you guys again.
So the statistics is never taken into account in this work, right?
What do you mean, statistics?
When you perform experimentally the procedure, you have to collect results in order to estimate the parameter that we have to put again.
No, because there they have the exact value of that. So computing the infidelity was easy. But I imagine that if you're like what I was discussing, if you don't know the ground state and you want to find something, you need to consider run with different parameters, because also I forgot to say this, but variational quantum algorithm is very dependent also on the initial parameters. So if you happen to put close to a local minima, then it can get stuck. So the idea is, ideal to make many optimizations and different initial parameters, which one wins, basically that.
Marcel, can I ask? Oh, no, sorry.
Sure.
Can I ask a question? So at some point, you said that they are using as in the middle of the evolution, they're using easy-like type of Hamiltonian, right?
Yes, because those. Let me go. Those are the type of Hamiltonian that they naturally have in their system. This is the Ising-like type of Hamiltonian, and this is the XX-like. So
I thought that I thought that they were sort of they could access only number conserving type of Hamiltonian. So that you are saying that they have access also to this XX. This is not number conserving, right?
But in the end, they can do this kind of plus minus and
plus minus.
Yeah, because they're dealing with qubits, but you can write this sigma x like a combination of plus and minus, right? So this is what they do in the paper.
Yeah, but to have XX, you have to have also terms which are not number conserving, I suppose, right? So I wonder.
Plus and minus goes to XX plus YY, no?
Exactly.
Yes, no. You're right. Yeah.
Quite, I think, quite outside of their reach, but they claim they can do that.
Yes, they do. They claim. Yes. I didn't do the calculations in detail, but I can check that later.
Okay. I wonder how. Okay, and they assume that they can feed the qubit. Somehow they can use they can make some unitary evolution on the single qubit, like phase evolution, and then feed back into the state of the system again, and then let evolve. That's the idea, right?
Yes, exactly.
This is the idea. Yes. Okay. Just because I missed the initial part. Okay, thanks.
Yep.
Any other questions? Okay. So if not, I don't know. It's part of the exams, right? It's part of.
Yes. Thanks, Marcel.
Thank you.
Now I and Luca will fill the. Come si dice? Verbale.
The certifies that you're good.
And we send